Indirect power control strategy for PV system connected to the grid. So there is contents introduction, literature survey, principle of indirect power control, result and discussion, conclusion and reference. Here introduction, traditional power generating using fossil fuel is unsustainable in long run and extremely dangerous to the environment. The main objective of the renewable energy are the reduce the dependency on fossil fuel and generate carbon free energy and can work as a source of energy indefinitely. Changing from fossil fuel to renewable energy cannot be done in a day or a year. It takes time to slowly increase the generation of the renewable energy, and that's why the wind energy system, solar photovoltaic system, biomass power system, hydropower system are being installed all around the world. Among all the renewable sources, solar energy is getting a rapid boost in installation. There is a PV system. After that, we can use boost converter and control by the MPPT control. We can extract maximum power from the PV system with help of the MPPT control. Then voltage source inverter after the boost converter. Then connected to the grid. Then the literature survey. The paper emphasized on the grid connection of the 100 kilowatt PV system to grid and helping the grid in destabilizing of the voltage by supplying variable reactive power at suitable conditions. This makes the system robust and stable and reduce the dependency on the grid reactive power supply. Every country has its own energy policy which detects the grid done to maintain the steady state operation of the grid. 100 kilowatt system can support the power use of 20 to 35 homes depending on the use of the power. This consists of PV system with the DC link capacitor and followed by the boost converter equipped with the MPPT control algorithm, which can extract maximum power from the solar panel. The output of boost converter is fed to the VSI voltage source inverter, which is controlled by the inverter control system. Unlike other control systems, the control strategy implemented in this paper provides the reactive power support to the grid at a variable power factor at different conditions for optimum operation. The power electronics devices used in the converter produce harmonics and consume reactive power which is drawn from the grid. But in this system, the reactive power provided that they reduce the stress on the grid and helps the grid to maintain the voltage stability. When the active power becomes negative and the reactive power becomes zero, the system operates at a unit power factor and DQ axis principle used in the wide implementation in the inverter for wind and solar application. This describes the system is following in German code which restrict the design to use only fixed reactive power, which may be vulnerable to system instability because at high voltage condition, reactive power needs to absorb and IQ component is made zero, which inject the power to the grid in a unit power factor and increase the stress on the reactive supply to the grid. The topology introduce harmonics in the system and the system as described above produce less harmonics and greater stabilization. Principle of indirect power control. System description in the PV system. PV system are combination of the solar panel which are connected in series and parallel to achieve the required current and voltage demand. Solar panel convert the energy coming from the sun to electrical energy, so its output depend on irradiance. Irradiance varies throughout the day, so the current, voltage and power operating point vary in the power curve and VI curve. Output current increase at higher irradiance and level linearly and voltage level increase logarithmically, but the irradiance change the surrounding temperature which also affect the voltage and current output. As temperature increase, the current increase but the voltage decrease, which decrease the power level. So the different MPPT tracker algorithm are implemented to operate at optimal operating point. MPPT and boost converter. MPPT maximum power point tracks point of the maximum power on the power curve by changing the duty cycle of boost converter. The boost converter duty cycle given by V output equal to Bs divided by 1 minus D and I output equal to Is 1 into 1 minus D. Then the input and output resistance relation is given by Rs equal to R output into 1 minus D square. So the input resistance can varies by varying the duty cycle of the boost converter, which makes the operating point of PV system at maximum power, and perturb and observe algorithm is implemented for the maximum power point tracking. Then the control strategy for three-phase grid-connected PV system. Conventional control strategy. The proposed control strategy to provide the control signal to the VSI so that it can connect the DC bus to AC bus. The converter introduces a lot of harmonics in the system. So before connecting to the grid, the output of VSI is passed through the filter, which reduces the harmonics by reducing the ripple in the current and voltage waveform. The normal control scheme compared the DC voltage, so the reference value to generate the error signal which is passed through the PI controller to produce the ID reference value, which control the achieved active power. Normally, the reactive power reference current is made zero to provide the maximum active power to the grid. In order to transfer electrical energy to the grid, the controlled way grid stabilization need to be done, which can be achieved by PLL phase lock loop. As the grid is reached with the harmonics and frequency, the amplitude detection can be difficult job. PLL provide the best result in the grid stabilization using the phase detector, voltage controlled oscillator and loop filter. Then the proposed control scheme. The control strategy described in this paper generate ID and IQ reference signal in a very different way. IQ reference signal is produced by the comparing the power output to the reference power, which generate the error signal which convert to the per unit signal and it then feed to the current controller. Next, the active and reactive power relationship can be defined as Q equal to P tan angle and phi is cos inverse power factor. The Q reference can be calculated from the P reference by using the formula. The variable reactive power support is provided in this paper at different condition. When the power is negative, the reactive power is made zero, which enable the system to operate at unity power factor. Q reference generation block also check the DC link voltage condition under which increase the reactive power to boost the voltage. At higher power fluctuation, the reactive power is set to zero until the fluctuation reactive power reduced. The block is also designed to minimize the fluctuation in the DC link voltage. A reactive power reference generating block is designed in this paper, which sets the reference value of the reactive power differently at different conditions. The IQ reference generation control blocks in MATLAB simulation. There is a IQ reference generation. Q reference is given 0 and there is a angle tan angle 50 and tan angle 25. Between the angle 18 degree and 71 degree we can choose the angle for reactive power control algorithm. In the reactive power reference control unit also have a PLL unit which consume the fluctuation in the DC voltage in term of the frequency and converted to unit frequency value and subtracted from the original control signal to provide IQ reference. As DQ reference is the static frame of the reference and the DQ axis is not coupled to the independent action can be taken and the DQ signal the according to and the formula used to IQ, the ID equal to P reference divided by VD and IQ is equal to Q reference divided by VD. So this formula is implemented in this MATLAB simulation and the current control module according to the current controller are implemented calculated static error between the actual and reference value. DQ reference frame mathematical model can be represented as ls plus r u minus omega l ls plus r L I Q L L Q V D and VQ. From the following matrix, it is clear that the control value are related to so feedback connected to introduce minus WL and WL. The grid voltage feed forward so that the IQ and ID can be decoupled. With the above matrix, mathematical modeling of the system can be easily. Then resultant discussion. The 100 kilowatt PV system under this studied has been modeled and simulated in MATLAB simulation at different solar radiance and the result of different parameters such as 3 voltage, phase voltage, current and power are analyzed and discussed. The parameter of the PV system are used in the simulation purpose and the radiance level are set to PV system under the different time horizon to analyze the system performance using the proposed control scheme. The radiance level input waveform of the PV level that are shown in the figure, then the radiance change with the second and the voltage and current PV panel, both the current and voltage are changing with the radiance accordingly. The PV voltage and current, the phase grid current waveform is shown in the figure. The behavior of the current waveform shown better transit response and less settling time in steady state and proposed control scheme. Similarly, the grid voltage behavior can also be seen in the figure 10. The dynamic response of the waveform is good and constant throughout the time horizon, even when the radiance is changing. Also, the above three-phase current and voltage initially produce the variable amplitude as its transient state, but the controller produce control signal which is smoothing the waveform. DC link voltage The DC link voltage waveform is shown in the figure 11. Then the voltage is constant even under the change in the source radiance and regulating power accordingly. The transient are present at the time of the change in radiance and rapidly, as settling down at reference value which show the first dynamic behavior of the control scheme. The VDC voltage output voltage of boost converter and PPV the power output, and desirable voltage wave and power wave from the boost converter is constant DC, but whenever there is a change of radiance level, controller takes some time to adjust the power and voltage level to constant. As we can see from the power level graph, the power level decrease with decrease in the radiance, but the voltage level remain constant at the duty cycle of the boost converter change to make the voltage constant. Then we can see the conclusion of this paper. This paper discusses the need of the reactive power regulation to improve the grid stability of power quality under the different variable conditions. The results are discussed and shown the improvement of the system response under the different operating and environment conditions. DC-link voltage waveform has shown better transient and dynamic with the proposed control of PV system connected to the grid. The scheme is also provided better transient and steady state response of active power using the indirect power control.